Hi, I'm Shawn Luke from DigiKey. With me today is Bob Card and Theo Kersjes from onsemi. Really excited to have this discussion about robotics and physical AI. There's been a lot changing in this industry, and these two guys are just in the perfect place to tell us more about what's going on in the industry. So Bob has over 30 years experience in the semiconductor industry. He's worked on brushless DC, motor control, lithium-ion battery management, USB-C power delivery. Bob has over 12 US patents. He's got publications and blogs. His current title is a marketing manager analog mixed signal group at onsemi. Theo has over 25 years experience in the semiconductor industry. Really grateful to have Theo here as well because he built the AMRs for onsemi. Those are autonomous mobile robots. So these autonomous mobile robots, he's got subsystems that has motor control, image sensing, and power conversion. So Theo's current title is Industrial Business Development and Solutions at onsemi. A couple other resources that I want to mention before we get started. We've got a wonderful supplier marketing center at digikey.com from onsemi. This doesn't just have the products, it's got videos, it's got 16 different solution pages, including one of the solution pages that's been created by Bob and Theo that's focused on the AMRs. Also, one other thing, we got the tech forum. It's a great place to have follow-up discussions or questions based on the discussion today. Want to ask you about robotics, because robotics has changed a lot in the past decades. Like, we've come from a place where robotics were really needing to be physically partitioned off. Workforce needed to be kept separate from the robots. Whereas today, there's a lot tighter integration where people are closer to the robotics. You've got AMRs working on the factory floors. You've got cobots working alongside someone in a work cell. What are the different design considerations that need to be made on today's smarter robots?
You want me to take that, Theo, or do you want to take it?
You go first, and I will go follow up.
Well, the first thing that comes to mind are just many more sensors because, the robots, like you mentioned, that are the industrial robots that have been around for decades, they're fantastic at what they do, but they're super dangerous for humans to be nearby. And so the notion of having robotics working more in harmony physically with humans brings up safety is really the number one concern, but many other benefits where the robot has a lot more sensors, and that includes like ultrasonic, image sensors, LiDAR, radar, to name a few, and they're all brought in together in sort of a sensor fusion to be able to, for the algorithm to be able to process that properly, and to be able to navigate around its surrounding environment, and that's the key. With these industrial robots. Like I said, they were great at what they did. However, they're not really designed to move around freely in their environment, especially if that environment is dynamic. And that's where the smarter robots come in.
Yeah, and to add to that, if you look at those original robots, they basically solved problems that humans can't handle, like picking up a whole car, heavily used in the car industry, or parts of large equipment and move that in the production line to some point, welding and also painting, paint booth. So things that are safety hazards or very repetitive work, that's where they started. And so they're in very tightly controlled environments like warehouses and, as I mentioned, assembly lines. And now to enable these robots to do even more things, they get into more flexibility, and that's where these sensors come in, where you can use a robot in the morning to tender a CNC machine, and in the afternoon it can do some packaging for you. So even smaller companies don't have to design the whole production line. They can get for their anniversary another robot and put it in their systems and integrate that, and that's allowed by this physical AI and robotics where we're at the moment.
So we've seen what AMRs can do. We've seen them be able to buzz around on the factory floor, relocate shelves and fulfillment centers. What's next for AMRs?
You see initially this in warehouses, again, controlled environments. Lighting is controlled, which is very important. If you talk about imaging sensors, if you get out in the sunlight or other environments where you don't have control, You might need features like high dynamic range in your sensors. And so when these systems get safer on people, which they're getting to the point that they can be used in agricultural settings, outside, delivery robots, and at that stage, you have to incorporate sensors that are able to account for those variabilities in the environment, as well as do more finer tasks like picking maybe berries or some other things. And that's, again, where you need force feedback sensors, rotational positioning sensing, and moisture sensing. And so that's where you see this explosion of sensors that come into this space to make these robots better at their functions.
And I think you're going to see an earlier ramp of robotics in industrial applications, in factories, doing many of the things that humans do. There'll be, robots will be able to come in and do this similar tasks. But then there's also going to be another wave coming where robots, I think, are going to be in the homes, and they're helping families do a lot of the things we don't want to do anymore. I don't want to go up and clean out my gutters on my second floor house. I don't want to scrape the paint off my house and then paint it myself. I would love to hire a robot, or purchase a robot, or rent a robot, or lease a robot, or hire a company that has robots that can do a lot of these things that I just don't like to do. As we all get older, we're physically less able to do many things, and robotics will lend a hand there as well. Dangerous jobs are great applications for robots. Security is a great application for robots. So there's a lot of, it's a very wide vista of applications for robotics, especially, like the more humanoid robot that is sort of acting and becoming more human-like.
Yeah, and if you look at a lot of the studies, this is where you see initially is where these robots are applied. For instance, there's now a trend to have autonomous forklift trucks, and it's basically out of safety necessity. When you look at the OSHA numbers, that about 35,000 accidents happen with forklift operators each year in the US alone. Those are staggering numbers. And then with the 40% turnover in those fields, to get a robot and have it do these type of functions is really increase your safety in these areas. And that's where you see it really first initially take root in things that we can't do. They're just too heavy or too big, or there's a big safety issue with us doing it versus a robotic system doing it.
And if you think about it, there's a lot of similarities between mobile robots and ADAS for automotive, and vehicles driving themselves, and a lot of commonalities in terms of the technology to make that actually work. But one nice thing about robots is they're typically moving maybe in 1 mile an hour, maybe 2 miles an hour, whereas vehicles are going 70, 80 miles an hour. And so in some ways it's not an easier, I guess it's an easier thing to figure out and get working, more of a baby step, if you will, than have ADAS working on our highways. So
yeah,
a lot of similarities.
Well, and to that point as well, what they always say is in industrial applications, if something is unknown to the robot or to the conveyor belt or to the automated system, it will slow down or even stop. And that's a tradition that now also moves into the robotic space with the robots in those areas. And in your car, of course, on the highway, you can't stop. You always have to continue and either get out of the way or do something. And so in that way, we have a little benefit with the track record in industrial automations to apply these systems in environments where we have a little bit of control over the environment. It doesn't have to be anymore in the warehouse, but if you have a security robot surveying your premise in your factory, you can safely know that there will be no people or kids running around there doing things to it or interacting with it. And so you still have control over the environment, which is a really good point.
Let's talk more about navigation and autonomous driving. It's just not a trivial challenge at the current time. There's this algorithm, the Simultaneous Localization and Mapping, SLAM. It's out there to solve this problem of navigation. Could you tell us more about what this is and how it works?
Well, it's very akin to one of us putting a blindfold on and being led into either a room that you're very, very familiar with or a room that you've never been in. And imagine trying to navigate that room. And that's just a relatively small space. And so all the innovation is really kicking in with this idea. And it's Jensen Huang really driving a lot of it with his digital twin and Omniverse, is this idea where you can model that room for your robot, and your robot overnight can train in the virtual room and try with just trial and error, really try a bunch of different iterations throughout that room, using that as an example, and overnight learn and go through 100,000 workflows overnight to be able to learn how to navigate in that room once you're fully deployed. So take that room and then flip it and turn it into a warehouse. And now you've got this really fantastic ability for self-learning if you can digitize that warehouse in the Omniverse, for example. And now that robot can learn overnight, or multiple robots can learn overnight, and they can literally learn with each other and not bump into each other in the virtual domain. So when they go into the real domain, they have all these, they've been trained.
Yep. This is another area where automotive has a little bit of a bigger challenge. They have the famous thing, which is the first car through. So you can make a very detailed maps and learn and have these in the car. But then the first car that encounters a certain highway where they just started building something and opened up the road and put new roadblocks up, that car has to do something special or encounter that and then can send it over the network to the other robots or other cars to update the maps and then be safe again. And that's where you see in automotive now focus on, for instance, freight liners, so trucks that go maybe from a shipping yard container to a warehouse, so controlled, again, roads. And in industrial applications, of course, we have that, again, inherent by having control over the environment and what's happening there. So very interesting topic there. Another thing is we, of course, use the robot operating system in our mobile robot. And this allows us to integrate sensors through technology that NVIDIA has called HoloScan. HoloScan allows very fast interface between high definition or high bandwidth sensors like image sensors to copy what the robot sees directly into the memory for processing, and with that reducing the latency. And those kind of things are very important for some other applications you saw or coming up, which is telemedicine, where you have a robot operating on somebody that are controlled remotely by a physician, and there you need the latency and the bandwidth of the networks to be very short, and it's also an upcoming technology. This then leads in maybe the last thing to mention about this, the partitioning of these systems. So in robotics and humanoids and those kind of systems, they now tend to have what they call System 1 and System 2. System 1 is basically the robot, if it's a humanoid, keeping itself straight, doesn't fall over, and has all the systems working that it can do that by itself. And you can then have a remote operator still to direct it to go walk in certain directions or do things, but it can keep itself upright and handle all its arm movements autonomously, kind of as a underlying System 1 system in the robot. And then System 2 is the navigation stack we just talked about, where you can give it higher commands like go and do something, those type of both of those systems are developed now in parallel, and that gives a very good separation of the functionality that you need for these robots to become safe and self-sufficient around us.
And speaking of image sensors, and one of the cool things about where we are right now in 2025 with robotics, in my opinion, 2025 is going to be the year of the robot. And it reminds me of when, Steve Jobs came out with the first iPhone. And he couldn't have done that if 10 or 15 different technologies hadn't reached some level of maturity and cost, right? Including the Gorilla Glass, the, internet access, the wireless technology, you can go on and on and on. And I think we're getting there with robots. For example, like with image sensors, you have a 2D image, right? You have your basically width and height, but you don't have depth, right? So sometimes you could use something like LiDAR, some kind of time of flight measurement like LiDAR or ultrasonic to help you with the depth. But one of the new innovations that we have is this new camera called ITOF, or indirect time of flight. And it's basically a regular camera. However, it's got some GPIO on the side, and that GPIO sends out a laser that's safe for humans, and it measures the time of flight of that laser going out and coming back. And it can measure depth up to, don't quote me, but I think pretty close to 50 centimeters from a pretty far distance. And so now, it's an important piece of information is depth. The camera, you could see two things, but it doesn't really know, how far away they are from each other without depth measurement. And that's being added. So you're seeing all these levels of innovation that are coming to fruition now and becoming more and more mature. And then it's all about AI. This ability for AI to come in with, like a ChatGPT AI or physical AI, is it can truly accelerate that learning process and training process for the robots.
Yeah, and it's interesting to see our customers working on their solutions and coming to us asking, hey, how can I solve this problem? And one is, for instance, looking under robots. If the robots are a little bit off the ground, further off the ground, they want to enlarge her. They want to see if there's anything underneath. And that's where we have, for instance, ultrasonic technology that can be used, as well as cameras. It depends on the price and the cost where you want to be with that solution. And LiDAR. And as I mentioned, there is now we have a force feedback, and this force feedback sensor also allows to do some distance measurement. So we have different technologies where people really start to ask, hey, I have this problem. I have an environment where there is some glass walls. Then image sensors might not see the glass. Ultrasonic sensors definitely see it, or mirrors. You might think of those mirrors in industrial settings where you look around the corner. So that these spherical that hang on the ceiling. Well, how does a image sensor system knows what it is looking at, and that something is coming at it from an angle? A drone might even think, oh, that's a window, I just fly out through it, if it only has image sensors. So that's why you want different sensor modalities. LiDAR laser will see it, but might get different reflections or refracted on the mirror surfaces. So there's different sensor technologies that are needed for all different use cases to make these systems safe and very effective. Yeah.
Great insights about the future of robotics. When you're putting together this design, it's chock full of interesting technology and new pieces. What are some that stand out to you, Theo?
So we come up with the idea because our customers are asking for the specific technologies or do more in that area. We can take a lot of leeway though, because of course safety issues, safety standards. I really want to demonstrate the technologies we have and use as many evaluation boards or sub customer products like image cameras, which are built using our image sensors. But I don't need to take every different situation into account. One example is, for instance, as well, if you have an autonomous mobile robot and you carry something on that robot, then the view is of course blocked for a LiDAR to do a 360 measurement. So normally these systems might have diagonally a sensor cluster in each corner to get a 270 view, and those things I don't have to take care of. So that's very nice. I can only focus really on the individual sensors and what they do. What we've seen then, as you already mentioned, things like e-views, things that we do which makes sense for power distribution systems in other contexts, are also very important in here. In particular, the capability to gracefully reset. If you have an e-fuse, you can have the CPU do something specific with it and reset the robot and get out of the way or do something else. And you can think about higher functions that you can enable with the technology, like e-views and charging and other power solutions as well. Yeah.
Well, one of the challenges too is, when you have some kind of product that's plugged into the wall, you've got an AC to DC converter and you've got some DC rails, and you can pretty much count on those DC rails being regulated. But when you have a mobile robot, you're running off a battery pack, and that battery pack, depending on the state of charge, let's say you have 10 cells in series, can vary from like 30 to 42 volts. So you need quality DC to DC converters, like we have the FAN 65,000 family. That's an excellent. It's a synchronous bucks that are well above 95% efficiency, that can deliver multiple DC rails for all the other subcomponents to run off of. So anytime your battery running off a battery, you could literally draw a line, connect the dots between the efficiency and the battery life. If you have an inefficient system for your DC to DC, your battery life goes down. If you have a very efficient DC to DC system, your battery life goes up.
Yeah, and I'm always very interesting to how can we show this to our customers also in the digital space and the Omniverse, ISIC simulation. Is there a way I can have the robot drive a certain path or do something and then tie that back into our very efficient MOSFETs, T10, our new trench technology MOSFETs, to show we have longer battery life somehow. And those are very interesting findings and discussions I have to be able to show some kind of these advantages besides pulse tester or some heat sensing through these products, to have them really in the system evaluated. Another thing which was very interesting and early on we talked about is that we work with the robot with different channel partners that might have also different line cards. And so there's a request, can we have our microcontroller system integrated or some of your onsemi sensors that are through our partners in that context. And so we designed a system that it uses a Docker container, Docker technology, to have the whole robot operating system running in a Docker environment that is then portable to these different microcontrollers. And we have quite a list, of course, the NVIDIA Jetson Orin development platforms, but the D3 Embedded has some nice systems that uses productizes these Jetson development systems. Advantech, Renesas, AMD all have their own microcontroller systems that we can then port to and have versions of our robot use in their environment. Yeah.
And another way that robots, or especially mobile robots, is similar to automobiles, is that robots for communication inside the robot, they typically use CAN for communication, which is a two-wire multi-drop communication protocol that allows you to communicate across multiple devices. And onsemi is an innovator, or one of the leading innovators, for a new technology called 10BASE-T1S, which is an Ethernet technology, but it does a multi-drop topology. So it's not point-to-point, it's multi-drop, just like CAN. And it goes over the same two wires, which are unshielded twisted pair, which is nice because you don't have a lot of weight and you don't have a lot of wiring. Real estate's at a premium inside of an AMR, but it runs 2 to 3 times faster than CAN. So CAN natively is 2 megabits per second. CAN FT can get as fast as 5 megabits per second if everything's running perfectly. But 10BASE-T1S runs at 10 megabits per second, and you don't have any gateways to go from CAN to Ethernet. And so when you have, something, these robots are getting more and more sophisticated. And so we're seeing a lot of traction, just in same thing with automotive, with zonal architecture. You're seeing 10BASE-T1S replace CAN in vehicles. You're going to start seeing 10BASE-T1S replacing CAN in robotics as well.
Well, I'm really excited to see this convergence of technologies. Bob and Theo, thank you so much for your time today. It's really exciting in the industry right now. We're at a place where you guys have pointed out the similar challenges that transportation is dealing with as the robotics challenges that you guys are looking at. This is a really great time. But also, it's just amazing to see stuff that used to be high performance computing that just only sat in the data center. That's coming down to edge workloads. The stuff that you guys have done with your NVIDIA and the different processors to figure out these challenges is huge. For those interested, please do check out the Supplier Marketing Center on digikey.com. Great references to help you build out your designs. Bob and Theo, thank you so much for your time. I'm really excited to talk to you guys again soon. Thank you.
Hey, thank you very much.
Thank you.